Hello, wonderful people. Welcome to Cosmology Talks. Today we have Jenny Wagner, who is at the Bahamas Advanced Study Institute and Conferences. She's talking today about the cosmological principle and observations that may or may not be indicating it isn't satisfied. So I guess the cosmological principle is a very fundamental bedrock to modern cosmology, and if it isn't satisfied, lots and lots of things would be possible that otherwise aren't possible, and analysis would suddenly become a lot more difficult because we wouldn't be able to use the simple metrics and things like that. But I'll let Jenny go into the details about exactly how we would need to change things. So yeah, welcome, Jenny. Do you want to start by telling us briefly about your paper?
Thanks a lot for having us, me and my 22 co-authors, to talk about these very interesting results that we got. And our title may be a bit boring, but it's actually a perfect summary of what we did in the paper. So our cosmological concordance model, the lambda cold dark matter cosmology, does not seem to be compatible with current observations and with data anymore. Many attempts have been put forward to resolve these tensions. Most of these approaches focus on, for instance, specific surveys like the Planck survey for the cosmic microwave background or the SCHUS dataset where we take a look in our close immediate neighborhood. Or we can also tackle different tensions that show up within lambda CDM, for instance, like the Hubble constant tension or the tension in the amplitude of the matter clustering. And here we have papers, for instance, like the Hubble Constant Hunter's Guide, the H0 Olympics, or Cosmology Intertwined, which tackle these issues. And contrary to all of that, we thought we should join several different probes from the early and the late universe to not only test lambda CDM, but to test the fundamental principle, like the cosmological principle, that underlies not only lambda CDM, but the entire class of all cosmological models, like the Friedman, Robertson, Lemaitre, Walker cosmologies, that lambda CDM is just one particular case of. And testing the cosmological principle, and thereby all the entire class of Friedman cosmologies, we found that there are actual residuals in all of the probes that give us hints beyond cosmic homogeneity and cosmic isotropy, and that there is no common trend in all of these probes, hinting at a very clear particular solution to all these tensions. So there is not a common forgotten systematic which clearly shows up by joining all of these probes. And this was the gist of our paper, to see, have we really forgotten some systematics which is obvious and which shows up by joining all of these probes.
So if people are thinking about this talk or your paper 6 months from now, and there's really only just two things that they're able to remember, what would you want those two things to be?
There is one take-home message which is methodological, and there's one take-home message which is clearly sociological and which has to be sociological. So let's tackle the methodological one first, because testing the cosmological principle compared to just testing lambda CDM is much more powerful. And that's why we went for the cosmological principle, because we are testing the entire class of FLRW cosmologies all at once, and not just every individual variation of lambda CDM one after the other. And what's pretty good, testing the cosmological principle is not as complicated as it sounds. So let me give you a simple example. If we take a look at the Hubble-Lemaitre law, h of t, then in all Friedman, Lemaitre, Robertson, Walker cosmologies, this h of t is parameterized by the same 5 parameters. And these parameters are taken at the time t0 today. So for instance, h of t0 today is the Hubble constant. This is one of the parameters. And we also have these omega parameters, which are also taken at the time t0 today. And now, if we take a look in our universe, in all the probes, then if FLRW is a feasible cosmology for us, then no matter which probe we take, at each cosmic time that we look at each scale, with each different systematics, with each different measurement uncertainty, we should always end up in the same 5 parameters, which we retrieve as a fit to these data. And so we would always get the constant values. This is a very clear test of the cosmological principle. And so for the second point, the sociological point of view, we see, and the community agrees, that these parameters do not come out the same for all of the different probes. And in particular, we have a tension in the Hubble constant between the early universe and the late universe. And so the problem here is, how do we proceed from here? There is no clear hint where the roots of this disagreement lie. Where can we find them? And so we have two options here from the philosophical point of view. Either we want to stick with the Friedman class and we keep lambda CDM or a variation thereof, but then we have to add systematic biases or extend into new physical areas, for instance extending the dark sector, or we abandon lambda CDM in favor of a more complex cosmology because we think that the systematics that we would have to add to lambda CDM seem to be physically unreasonable or seem to be implausible for us. And when we wrote this paper, we thought that the community is actually split into these two camps, and we do not think that there will be an easy agreement because each camp just comes up with new data evaluations trying to convince the other camp, no, please stay in lambda CDM and stay in the Friedman class, and the other says, no, it's a clear hint against this. And so I think the main take-home message here is that we should now define limits up to which we are willing to keep lambda CDM or the Friedman class, and we should look what are clear observational hints for us that bring us to abandon lambda CDM and to say, okay, this is a clear hint for more complex cosmology. And I think the gist of our paper here is to say we have a look at all the probes, and it is pretty clear there is no common systematic, so we have to have this discussion now before we go on with further evaluations to really clearly define what are the rules of the game, when do we abandon lambda CDM, and what are we still willing to include.
One technical question already. You said that within FLRW, h of t can always be explained by 5 parameters. That seems counterintuitive to me because I could have matter, radiation, and 20 different evolving dark energy parameters. You know, so the Friedman equation is h squared equals rho, right? And the rho could have 100 different parameters. So what are the 5 parameters that I can use to simplify that?
Yes, I mean, let's put it like this. I was thinking about like the standard Friedman cosmological models that we have, which are based on the physics that we see so far. And so I would say we take H0 as the Hubble constant, and it's a kind of like normalization factor in front of the expansion function of the universe. And for the expansion function, we take omega m, like the matter parameter, we take a curvature parameter, we take a radiation parameter, and of course, I would say, just based on Einstein's field equations, we take omega lambda as a constant.
Sure, so I get, but you could get rid of lambda CDM, but keep FLRW and have other parameters in there. I mean, things like these early dark energy models are doing exactly that.
Right. I mean, how you parameterize in the end is up to you. You still have this degree of freedom, but I would say in the most simplest case, based on just plausible stuff that we see and that we know that has been established for the last 100 years, I would stick to these 5.
Do you want to get into the background now about why you did this? I guess you went into that a little bit with your 2 takeaway messages, that one of the reasons to go into this is there are all of these tensions, and as you said, conceivably possible that there's different systematics in all of them. I mean, astrophysics is a messy thing, but it's also conceivably possible that, our framework model is in some way oversimplified. A very good model, it's not completely wrong. Like when we extrapolate the early universe to today, the expansion rate h changes by many orders of magnitude, and then we're off by a few percent, but we are off by a few percent. So obviously that's a motivation you've already given, but what else makes this relevant in 2023?
Well, I think we are 23 authors, so each one of us had a different motivation or slightly different motivation. For instance, you can start by saying, I would like to solve the Hubble constant tension, and thereby it's pretty efficient to study the cosmological principle because I get all the other models in the class as well. Or you can say, I can see this as a motivation to study the cosmological principle, to understand the role of lambda a little bit better, like what is the interpretation and what role does it play here. This is another motivation. But for sure, I mean, all of us are interested in finding out whether a 100-year-old simple cosmological model is still sufficient to capture the details of the current sky surveys. And I think, why is this done now? I guess the fact that we have several discrepancies, for instance, like the Hubble constant tension, and these discrepancies now pass the 5 sigma significance threshold. And I think this is an alarm bell which now starts ringing louder and louder. And before our paper, there were a lot of papers tackling just the individual parameters of lambda CDM and discussing different sky surveys. And a few weeks after we published or submitted our paper on arXiv, Jim Peebles published a similar review in exactly the same direction, wondering whether we should abandon lambda CDM and what there is to extend in order to get a better model and to resolve the tensions. And a few weeks after that, the Euclid collaboration came around with a paper on how can Euclid test the Copernican principle. So I think we are now starting to get a little bit more generalized, just going away from lambda CDM and perturbations of lambda CDM to more general classes of models. This is more or less hanging in the air, and I think maybe this also nudged the European Union to approve the establishment of a research network, which is called the Cost-Action Cosmoverse, in order to coordinate and to bring a systematics into all of these approaches, that we do not search for a needle in a haystack.
Depending on exactly what you mean by lambda CDM plus perturbations, I feel like huge chunks of the community are considering beyond lambda CDM, dark sectors, early dark energy, dark radiation. But going beyond FRW is a rarer thing that may indeed be the case. I guess the reason I have always kind of assumed that people could go beyond lambda CDM without going beyond FRW is just mathematical simplicity. If I add in early dark energy, I can sit down and pretty quickly calculate my new H of T. But if I say I'm going beyond FRW, it's very difficult. Unless you come up with a kind of toy model like a Bianchi universe with an anisotropic, but still just one axis is different to the other axes, that's very easy to just write down and then calculate. But if you go completely beyond FRW to just a more completely generic metric, it becomes extremely difficult to calculate anything, despite the fact that it's probably just as well motivated as adding an additional like matter or gravity degrees of freedom.
Another motivation is to start, actually, when we take a look at our simple cosmological backward model, it has passed a lot of different consistency tests. But we shouldn't forget that it has been developed 100 years ago as a very simple model. But already then we had different tensions, and people were expecting that these tensions, if for instance in the Hubble constant, there's always been going on, then people were expecting that with more data we would actually solve these tensions. But to the contrary, now they are aggravating. And I think that this also happens because people are now aiming for percent precision cosmology. And now the precision is so tight that actually the different models matter. And so I think this is also why now we can ask, are we actually at a measurement precision where we can probe hints beyond homogeneity and isotropy? And I think we are in this data-driven era now, so it makes sense to do this. And if we would like to do this, we have to pragmatically ask, how can we probe inhomogeneities and anisotropies? And this calls for a very precise definition of what is the cosmological principle. What do we mean, or what did Einstein mean when he said that the universe should be homogeneous and isotropic? This is not clear a priori, and I think hardly any physicist thinks about this problem. So the formulation of the cosmological principle is already fishy. And we tried to find a more precise definition, and I was really happy to get support from the philosophers and the historians of cosmology from the University of Bonn around the group of Dennis Lehmkuhl, and in particular Niels Martens. He had a seminar on similar topics, and we discussed this, and I think we succeeded in finding a very sharp terminology as a very first step to ask, what are we actually testing when we apply a certain probe to test the cosmological principle? We need to define what is the cosmological principle. And Einstein in 1917 said, all locations in the universe are equivalent. In particular, the locally average density of stellar matter should therefore be the same everywhere. And there's a lot of knowledge in here. And then Friedman later used this. He got inspired by the class of different solutions for Einstein's field equations, and he said, how about I assume a very simple model and I assume that the metric is exactly homogeneous and isotropic. And he found that in that sense he can solve the Einstein's field equations, and this is a very simple geometry. But we shouldn't forget, on the other side, on the right hand side, we have a matter density tensor, so an energy momentum. And this, in order to be a cosmological model, needs to be consistent with homogeneity and isotropy. And here we have three different options. The first one is, it's an exact homogeneity and isotropy on large scales, meaning we define a scale of homogeneity, and above that, we say the Friedman equations are a valid description for cosmology, and so above a certain scale, then we have exact homogeneity and isotropy on the left-hand side and on the right-hand side. But Einstein said something different. He included our point as an observer, and he said, let's define a large enough volume, and averaged over this volume, we see statistical homogeneity and isotropy. And then, of course, we can also say, let's take this only up to the measurement precision to include our limitations in the data acquisition. So that's from the theoretical side. But now we still have to remember, we want to put data into this. And this is, I think, the gist, how to define now cosmic homogeneity and isotropy in order to test it with data. So first, we have discontinuous data, which are granular and which are sparsely distributed, maybe not even equidistantly. So we have to find a sampling hypothesis and then see in how far they actually give a homogeneous and isotropic energy momentum tensor. This is what I call the matter sector test of cosmic homogeneity and isotropy. And assuming we have this, then we can go on and plug this T mu nu in the right-hand side of the Friedmann equations, and then we can probe the geometry. Then we can ask, what G mu nu do we get, or what properties of G mu nu do we get based on this T mu nu? And this is what I call the space test for cosmic homogeneity and isotropy. And in the next slide, I have some examples, and I will detail this later in the talk. But for now, I just want to mention that there are for both regimes, we have tests, and we actually test these two different regimes with different probes. But we should remember that no matter what we do, we have a bit of a chicken-egg problem here. If we would like to test whether our data are homogeneous and isotropic on the matter sector, we implicitly need to make assumptions about the space-time geometry. Think, for instance, about clustering and about structure growth. How can you look at clusters if you do not have a notion about volumes and about distances? So there is an implicit assumption going in there. And on the other side, if we would like to probe the space-time geometry, then we need to have a sampling hypothesis how these observables, discontinuous observables, sample our continuous T mu nu. And so we cannot test both at the same time. And this was one of the points that we found during the writing of the paper, that actually different probes test different things for different parts of the cosmological principle. And we have to disentangle that. And another point, which we also found was pretty interesting and maybe not clear to everybody, was, I mean, it's an old thing. It has been put forward by Ellis and Stöger in 1987, that we are actually having a fitting problem in cosmology. And all the signals that we have are underdetermined, in the sense that we're measuring a signal and we partition all the individual parts of the signal based on what is the intrinsic mechanism to emit the signal. The signal will then propagate over the space-time metric. And on top of that, we have a perturbation level, like normal astrophysics, where we have biasing obstacles. For instance, we propagate a signal along a homogeneous and isotropic background metric. And on top of this, we see dark matter clumps or luminous galaxies, whatever. And all of this together, in the end, gives us our signal. So if we fix cosmology, then we can study astrophysical effects. So for instance, we fix the background cosmology, then we can study the properties of Cepheids, supernovae, gravitational lenses, you name it. But now, if we want to probe cosmology, we need to put the cart in front of the horse in some sense. So we need to calibrate all the data acquisition and all the astrophysical biasing effects of the perturbation level together in order to actually probe cosmology. And here I think we have this underdetermination problem that we shouldn't forget. We can add systematic biases to a very simple space-time metric, like a Friedmann model, or we can interpret the entire signal as a more complicated geometry, a more complicated cosmology, and then hopefully make our biasing obstacle sector or perturbation level sector a bit simpler. So in that sense, we are just probing a complex universe, and we can ask, how complex is this universe? Is the fit with lambda CDM still sufficient and we can add some biases? Or do we actually need to go to inhomogeneous anisotropic cosmologies?
Yeah, I mean, maybe you'll get into this later, but the question of going beyond homogeneous isotropic is in what direction, and can an observer write down a simple, it doesn't have to be simple in a kind of like a calculationally simple, but simple as in just a few extra parameters to fit to model. And then if that's true, then I guess it just becomes a case of persuading people to do that or doing it oneself. But otherwise, yeah, like I think that they're always hamstrung by the fact that it could be beyond FLRW in a continuous infinity of different possible ways.
Yes, right. I mean, for instance, the next to leading order approximation to these FLRW models would, for instance, be dipole models, like Bianchi models, where we have just like a simple one direction in anisotropies. Shahin Sheikh Shabari is currently drawing up a research direction in that sense, that he says, let's go to next to leading order beyond Friedmann model. But I think it could be anything. And so in order to kind of like say, let's see what the data actually constrains, we should be like perturbed Friedmann models or even just a little bit beyond that. I think there's also the approach that we say we make just like an expansion in any orthonormal basis function. For instance, Asta Heinesen is developing such an approach. You had her on the call. And I think such approaches are also pretty interesting to see what is the constraining power of the data. And I think if we have both, if we have the modeling coming from like physical motivations, and if we have, on the other hand, like the pure mathematically driven approaches to what can the data constrain, if we combine this, I think we gain a lot of insights into what's actually there.
Yeah, no, that work is very useful.
And I think if we are thinking beyond FLRW and the universe actually is FLRW, we will end up again with this simplified model, but now from a more general viewpoint that we actually know there is not much more. So I think coming from top down, saying, is there something more general, and we find, no, there isn't, this is much more reassuring than just perturbing or going a little bit beyond FLRW in the sense from inside and not from a more general viewpoint. I mean, that's why I am looking into this, because I think we should think a little bit more general. And if the universe is FLRW, we will end up again in exactly that.
Cool. All right. So that's a good motivation about why we want to test whether homogeneity and isotropy are valid in our universe, and I guess also from our position in the universe. Tell us about the results and whether we are in such a place in such a universe.
Now to the actual probes that we had in the paper based on the framework that I just sketched. I mean, what are we actually testing? So, of course, we have a lot of different probes and we investigated a lot of different anomalies in the paper. And we also had the discoverers of some of these anomalies actually as co-authors, which helped quite a lot to tackle the systematics and to discuss this from both point of views. Like, should we stay in the Friedman class or should we go beyond the Friedman class? And so here I would like to start with a very simple first case, namely the cosmic microwave background, because here we are at a very peculiar redshift. We have an all-sky dataset which has been taken by one satellite, namely the Planck satellite. And so now we would like to ask, how can we constrain the FLRW parameters from the cosmic microwave background? This has been done by Planck. We have a full sky analysis, and from the full sky analysis, we get a certain parameter value for all of the parameters. And we get confidence bounds based on the systematics and on the measurement uncertainties and so on. And now we have this paper by Yang and Chu. The reference is given down here. And these guys thought, how about we do a jackknife approach? So we take the full sky data that we have from Planck and we divide it up into half skies. And we ask each half sky, what parameters can we get from the half skies? And then we can ask, do these parameter values agree between the northern and the southern hemisphere? And in order to get a bit statistics, they divided the entire sky into 48 half-sky analyses, meaning that they took different directions and then defined the northern part and the southern part, and looked in how far do the parameters agree, or is there a dipole in each individual parameter. The results you can see here on the slide. Of course, we see an anomaly, otherwise I wouldn't show this example. But we have here that the parameters, so here are the parameters that can be constrained from the power spectrum of the cosmic microwave background. And in addition, we also took H0 because H0 is a very important point for the Hubble tension that is one of the decisive anomalies that we have. Yang and Chu concluded that there are discrepancies in the parameters compared to the one in Planck. So there seems to be an anomaly, and the half-sky analysis does not coincide with the full sky analysis as done by Planck. So this is just neutrally what we get from this analysis. Now I would like to put my inhomogeneous cosmology hat on, and I would say, if I were in that camp, I would argue, look at this anisotropy. We have huge error bars here, so we could say that Planck was too confident in giving error bars which are too small, and here we see much larger error bars. So we can say that maybe Planck underestimated the errors and should enlarge them. This would also solve the Hubble tension, or at least alleviate it.
Can I just make sure I understand? So the different blue bars here are what?
The different blue bars are, if you take the 48 half-sky analysis and you look whether there is a dipole in each of these half-sky analyses, so whether the parameters agree or not, and in which direction and which amplitude, and then you make an average over all of these 48 half-skies, and you plot the variance as the confidence bounds here.
Of the dipole in, for example, omega b h squared. Okay. And unlike the dipole in the temperature, we shouldn't have a dipole in these parameters.
Right. We expect that if we live in an FLRW universe, the parameters should come out as being the same no matter where we look. And this is why we could say this hints at an anisotropy. Maybe Planck was overconfident, so this would say we would need to increase the confidence bounds for Planck. Or we say this clearly hints at a problem in FLRW, that this anisotropy here is actually a hint for an inhomogeneous anisotropic cosmology. And here we could also add that there has been this hemispherical power asymmetry, which has already been found in WMAP and in Planck, where we see that the northern hemisphere seems to show a smaller variation in the temperature fluctuations than the southern hemisphere. And so we could say the directions align, and so there is a conspiracy for a beyond Friedman model. This would be from the inhomogeneous cosmology camp. But now you can also be in the mainstream, and you can say, I would like to keep lambda CDM, and I can argue here for this analysis, look, we have 48 samples here, which is a very sparse statistic. So it's pretty clear that the error bars of this very sparse statistic will be huge. So this is one point. And the other point is when we are chopping up the full sky analysis into these half skies, and we are then rotating and taking different directions, we are actually analyzing the same data. And this means we have correlations in the data which are not taken into account in this more or less independent analysis. And maybe after cross-check, including this systematics, the discrepancy will disappear. So as you can see here, I mean, we do not have a really significant anomaly here, but depending on which storyline you want to take, you can argue that there is a hint for beyond FLRW, or you can say, let's take a look at the correlations in the statistics and in the methodology, and then the effect can go away, probably.
Sorry, I'm still a little confused by the error bars. So I guess I'm getting confused by the fact that, as far as I understand, two things are kind of trying to be described by the plot. One is the location of the dipole, and one is the variation in the actual parameter, or are these error bars in where the dipole is?
No, the error bars are just the variance on the mean dipole. So you determine from all the 48 half skies, you determine the direction of the dipole, averaged over all the 48. And then you say you take the variance over that to get an estimate on the confidence bound.
Okay, and so then each parameter has a different dipole. And the claim is that these data points are inconsistent with each other because they look, based on the error bars, to be consistent.
Yes, based on the error bars, there is, I mean, it's like 2 sigma discrepancy. So it's not significant. It's very small. But still, there is something which is showing up. I mean, the sigma 8 tension started in a similar way, and now we are kind of like increasing. That's why they published it, and they said, if we take a look at this, we do not see an obvious discrepancy. We do not see whether there are some systematics playing in that. I mean, we forgot because they used exactly the same pipeline as Planck.
No, maybe this is where I can give my typical speech about my perspective on anomalies, which is because of the look-elsewhere effect, most anomalies will turn out just to be either a statistical fluctuation that when you analyze enough data, you expect to find statistical fluctuations, or a systematic error because when you've got finite, flawed human beings, we're going to miss stuff that we should be adding to our analysis. And so when you have enough human beings analyzing enough stuff, eventually someone's going to make a really, really subtle mistake that the rest of us can't work out, and there'll be an anomaly. So that's why most anomalies actually aren't evidence of new physics, no matter how many sigma one gets to. However, what's also true is that whatever new physics comes beyond lambda CDM will show up first as an anomaly. I personally view things like the Hubble tension and the S8 tension as slightly more likely to be true just because the look-elsewhere effect there is slightly smaller. Before they went out and measured it, they said, we're going to go out and measure H0. We're going to go out and measure S8. There was an a priori motivated, this is the thing we're looking for. And we've got 7 lambda CDM parameters, and these are 2 of them. And then they found this discrepancy. Whereas something like this, even if Jung and Chu said, this is the thing we're going to look for, there's such a huge population of cosmologists who all have their pet things that they want to look at. And if 99 of them don't find anything, but one does, that one writes a paper, which, not saying that one group did anything wrong, it's just that cosmology community is big enough that one person will find this kind of fluctuation. So there is a bigger kind of look-elsewhere effect for a statistic like this, because there's lots of other things one could have chosen to do. Again, that doesn't mean one just completely throws this away and says it's not interesting. One then follows it up and says, okay, is this random statistical chance, or is it just this kind of statistical and systematic look-elsewhere effect that I've just described?
If I had to attack this analysis, I would say it's a sparse statistic with 48 data points. I would say normally if you're doing an all-sky analysis, Planck has pipelines with, order of 10,000 different universes in order to get like confidence bounds. And here we have 48 jackknife approaches just with half-sky analysis. And maybe there are even correlations in the data so that they are not independent. What would you say about this hypothesis? Is this possible that this is also an effect here?
Yeah, what I would do if I had an infinite amount of time to work on everything and then decided this was one of the things I was going to work on is, I guess I'd ask the question of what physics might be causing this, and then if I find models that I think are compelling that might be causing this, what other things will those models be producing? Go look for that thing. If I find that thing, then that adds weight to the possibility that this was also genuine. And if I don't find that other thing, then it adds weight to this being potentially just a result of this look elsewhere effect.
Yes, so we agree we need physical reasons why we should expect this. So now we can come to another test. So let's jump from the early universe to the very late universe, and let's do our first meta test. So the first meta test, I think, is pretty reasonable to do the scale of homogeneity. And in simulations from Friedman universes, which are our calibration stick, we think that we have a scale of about 370 megaparsecs, which is the limit of structures that we think lambda CDM and Friedman models can build, because we have a finite time, we have a certain structure growth history, and so 300 megaparsecs is the scale of a structure that we would expect to be very huge and large. And when Laniakea, our local supercluster, was discovered, this was already thought like, oh, this is a huge structure, and it had an extent of about 160 megaparsecs. So this is totally in agreement with our scale of homogeneity. We still see structures below this 370 megaparsec scale. But now, if we take a look further, we have the 4 largest structures in the universe. They definitely are in tension with this 300 megaparsecs, because this largest structure, the Hercules Corona Borealis Great Wall, has an extent of about 3 gigaparsecs, so 1 order of magnitude larger than that one. And we have the giant gamma ray burst ring, which has a diameter of 1.7 gigaparsecs. And we have the huge large quasar group, which has an extent of 1.24 gigaparsecs. And most recently, we have the giant arc, which has about a size of 1 gigaparsec. And you can see the giant arc on the top right of the slide here. And Alexei Lopez and Roger Clovis are co-authors of our paper, and they wrote a section on the giant arc. And you can see here that all of these structures are definitely in tension with this 370 megaparsecs. But the first 3 are already discussed and disputed to be chance alignments, either in space or in time, because the excess of gamma ray bursts that have been found for the structure number 1 and structure number 2, you could say this is just like a chance explosion of, a correlation of explosions in time, or it's even a correlation, just a chance alignment along the line of sight that we see them clustered on the sky. And for the huge large quasar group, you can also do similar arguments to say, based on the clustering algorithm and based on the statistics that you do, this needn't be an actual true structure. This still could be a chance alignment. But for the giant arc, maybe it's just too new. These debates have not been going on so far. And I think this is because the giant arc has the advantage that we have 2 different independent probes. We have the magnesium-2 absorbers and we have quasars, which are in the same area on the sky and which are also at the same redshift. So we have 2 probes hinting at the clustering. And Alexia and Roger used a lot of different clustering algorithms to also show that it's robust against different approaches. So no matter which clustering algorithm we use, we always end up in the algorithm finding this structure here. So if I put on my hat for the inhomogeneous cosmology camp, I would say we have a statistical significance from 2 independent probes. We have a robustness against different algorithms to cluster. We have different statistics to say how significant is this structure. So is it really above the noise level, above the chance alignment? And we find, yes, it is. And so we could say this is definitely a structure which challenges our Friedman models. And for instance, there are other groups hinting at self-similar cosmologies, like for instance, Yuri Barishev or Francesco Silos-Labini. And they say this is exactly what we expect to see. And they also have like more data sets to say, look, we do not have these large structures, but we see hints for self-similar structure growth. So why not? Actually, this is what we expect to see. So this is from that side of the camp. But now, taking the mainstream look, it's also possible to keep lambda CDM in the Friedman model, because we can argue, let's wait and see whether there is some further dispute on the giant arc, because the other ones, there need to be follow-up observations to confirm that they are actual structures. And so far we could say they could go away. And even if they stay, we can still say, what about we interpret our universe as one statistical realization of the entire class of Friedman models? And so we are not at the ideal Friedman universe, like in the total fair sampling hypothesis. We just have 4 structures which challenge the Friedman paradigm, but it's just 4. It's not like a huge number. So we are still close to an ideal Friedman model. And in that sense, we can keep our standard model because we say we just have these few structures and this is fine within my statistical assumption that we live in an almost Friedman model.
Yeah, so I haven't followed this since about 2013, but I did actually follow this reasonably closely back then. I wasn't very convinced at all about things like the huge, large quasar group. And I think that the scale of homogeneity statement that it should be of order a few hundred megaparsec is about a specific way of measuring homogeneity, right? Something like laying down spheres, and when the spheres get bigger, the variance of the density within the spheres should go below 1% or something. So the fact that that statistic should reach homogeneity at a few hundred megaparsec doesn't say anything about other things. And so the way that the huge large quasar group was found was not by dropping spheres down. It was a particular algorithm about finding friends of friends, neighbors, that sort of thing. In order to make the analogous statement, you need to take that algorithm and apply it to simulations that were homogeneous and see what the largest size objects it finds in an actually statistically homogeneous universe that you made from scratch. And when you do that, you do find things of order 1 gigaparsec. So the homogeneity scale for that particular statistic is of order a gigaparsec, in which case finding something that's in order a gigaparsec, it's not saying that that thing doesn't exist. So looking for it in multiple probes, you expect to find it in multiple probes because you're not saying that these quasars aren't real. You're just saying that this is not evidence of lack of homogeneity. And so I'm completely unaware of the giant arc point number 4. But if it was done in a similar way to point number 3, it's exactly the same thing. You shouldn't be surprised that that particular algorithm finds things of order 1 gigaparsec, because I remember there was a paper by Seshadri Naditha where he actually even randomly Poisson sampled. So it was a universe that was actually perfectly homogeneous density. There were no density fluctuations. And then the tracer was just placed completely randomly. So it's more homogeneous than our universe. And then he applied the exact same algorithm and found things this big. So in a more homogeneous universe, you expect to find things like point number 3.
I mean, on the other hand, what I found in these simulations, I mean, the simulation for the 370 megaparsec is by Yadav et al. From, I think, 2006 or so. And as I said before, when I told about the definitions of the cosmological principle, you need to have an understanding of what volume means and what distances mean. And in that sense, I think you are already making an assumption about, I would say, homogeneity and isotropy on the geometric part of the metric. And so I think the question is this possible to go beyond this 370 megaparsec and not be inconsistent in your team you knew? I mean, there, I think for the simulations, you have this trade-off that you're using this homogeneity in the simulations, and maybe this impedes you from getting farther than 370 megaparsecs. But if you started with, I mean, a full relativistic simulation, because normally we just use a homogeneous background and we propagate this, and then we have the clustering on top in a Newtonian fashion. And if we do a fully relativistic simulation, maybe we could actually prove that even if we have an FLRW class, we still get this 1 gigaparsec. I think the next 2 points that I have on my list, I mean the last 2 points, I think they are more bothersome because if we go now to my second space test, I would now like to see, is there a unique set of FLRW parameters across the cosmic time and across the scales that we have? When we start at the cosmic microwave background, we have rather homogeneous and isotropic structures. And so fitting an FLRW model to these structures is pretty easy. And then we evolve these structures forward in time in order to get the parameters for our model as inferred from the cosmic microwave background. And now we compare this fit to a fit where we first evolve the structures and then make a fit of a homogeneous and isotropic background plus a perturbation level at late time, so at more or less redshift 0. And there we have a huge perturbation level. It's not easy to fit a model again at this stage. And there we have the fit of the evolution of the structures. And in order to make sure that we're actually probing the same background, we have to take into account that we have to synchronize the probes, like I told you in the antidetermination problem, that we're actually probing the same cosmology. And I think a priori this is not clear. For me at least, it's not clear whether we're probing the same.
Yeah, I mean, I guess within the FLRW model you are, but within the space of all models, including the one that may or may not describe our universe, yes, it could be that.
And I mean, based on the data that we have, I mean, on the telescopes that we have, we also have to calibrate all the different data acquisition tools with respect to each other and the different systematics on the perturbation level, where there still may be ununderstood physics. So calibrating all of this together is difficult. And so if we now take a look at what do we get if we just use all the probes that we have and we ask what parameters do we get, we can make the following statement. Let's, for the sake of simplicity, stick to H0 and ask, taking a look at the early universe from Planck and taking a look at the Schuss data, we know that the two Hubble constant values do not agree with each other. So based on CMB versus Schuss data, we have a discrepancy of more than 5 sigma between early and late universe. But now we can also ask, what about anisotropies? And here, I think one of the most interesting research has been done by Kostas Mikas and his team. They used galaxy clusters as standard rulers and standard candles because you can measure their temperature profile in the intercluster medium. And this is a cosmology independent probe. And then you can also measure the extent, and you can also measure the luminosity of the cluster and the Chernyaev-Seldovich effect. And both of these give you a distance to the cluster, which is cosmology dependent. And so in the end, you can set up cluster scaling relations, which more or less standardize these galaxy clusters. And then you can ask for 570 galaxy clusters as they had, is there a variation of the velocity of these galaxy clusters, of the peculiar velocities, or in the Hubble constant, depending on how you interpret this, excess beyond homogeneity and isotropy. And then you can ask, if I take a look at different directions in the sky, is H0 always constant, or do I see some bulk flows? Depending on whether you want to see it as a bulk flow or in variation in H0. And they found as well a more than 5 sigma discrepancy across the sky. And they didn't expect this. Actually, it was planned as a cross-check. Let's see whether it's homogeneous. It was like let's start with that. And then they found this. And Kostas told me that they wrote like 100 pages of paper trying every kind of systematic. Is the temperature profile overestimated? Do we understand our Compton parameter? Do we understand the luminosity in the X-rays? And still the effect is there. Then they used the eROSITA dataset. This is, I think this is still unpublished, but he showed it already in a conference last year. And even if you add the eROSITA dataset, the effect is still there. So it's not vanishing, it's still at 5 sigma discrepancy. You can also take a look at other probes. For instance, strong gravitational lenses. We just have a few of them, so significance is very low. And for the supernovae, we face exactly the same. But again, we see slight trends that there is an anisotropy.
With the strong gravitational lenses, this is the time delay measurement of measuring H0, where I think we have a talk on that as well by Simon Birra, where the distance is measured essentially by the time delay of multiple images that have been strongly lensed. Okay, yeah, and then the supernovae, I guess, multiple talks on how you measure distances with supernovae, and you gave us a good description of the galaxy clusters.
And for the strong gravitational lenses, I happen to be an expert on that as well. I started in that, and I actually doubt that the strong gravitational lenses are a good probe for H0 because we do not understand the profiles of the mass densities there. So I think we still have to do a lot of good job in galaxy evolution studies to know what inhomogeneity we have in order to actually probe the background cosmology with these time delays. I think there's the big bottleneck there. Yeah,
there was this update they made where they updated their models of the density profiles based on some data they took, and their H0 measurements went from matching Schuss to matching Planck almost. I guess I'm oversimplifying, but it was
No, it's true. It's actually true.
Yeah, it made one more skeptical about their results after that.
Let's put it like this. I have an explanation and I'm working on a better understanding of these mass density profiles. So I can derive the NFW profile from first principles. But, this is still a far way to go because if we want to precision cosmology, the NFW profile is way too crude. And if we can explain these power laws, we still have to go to much greater detail. So I would say, with my approach, we can go down to like 10% precision, but 1%, I do not know whether this is feasible so far with what I understand from this.
Let's say that the strong gravitational lenses, there aren't enough of them, and so not look at them. But the galaxy clusters and supernovae, a priori, I have no reason not to trust them. Are they at different redshifts? And or if not, wouldn't one expect, if there's a great honking 5 sigma dipole in the galaxy cluster indicating a bulk flow, you should see it in the supernovae too. And it seems that if there is a dipole in the supernovae, it's not in the same direction, or is it in the same direction? And I'm just not reading these plots correctly.
No, you're totally right. And I will show you, in the end, I will show you a summary plot where all the dipoles are and in which direction they show. And actually, it's not the same direction. And you can also ask, there was this dark flow by Kaszlinski and colleagues. And you could also ask for the galaxy clusters because they could be at a similar redshift. In how far does this coincide with the bulk flows? And it's close, but it's still a little bit different in the direction. So actually we have different directions here. If I put now on my inhomogeneous cosmology hat, I can say we have deviations at the 5 sigma level in multiple probes. I mean, not just in one. We have discrepancies between early and late universe. We have discrepancies over the sky. And so this is a clear hint we should abandon lambda CDM, because clearly H0 is not constant. So what are we doing here? I mean, this would be like the most extreme inhomogeneous cosmologist driving this in favor of abandoning lambda CDM. But I think here is a huge caveat in this analysis, because you can say, if we take a look at what we are actually fitting, we are fitting different probes, different systematics at different scales. I mean, we have more or less point-like supernovae compared to all sky CMB, and we're fitting at different redshifts. And this altogether means that the data we have is not equally sensitive to all the parameters that we probe. And so we can say maybe we are at the 5 sigma significance level, but do we really probe H0? I mean, for instance, when we take a look at Adam Rees's papers, he looks at H0 in our local neighborhood. And actually, his data set is more or less not sensitive to anything else. It's just H0. And if you go a bit farther out to the Hubble flow, you probe a little bit of omega m. But you actually need to synchronize with the full Pantheon Plus from the other side. And it's questionable whether this is still enough, or whether we should go out to higher redshifts to synchronize the probe in order to actually see all the degeneracies between H0 and all the other parameters. Because H0 is the overall scaling, and if we fiddle around H0, we can also fiddle around omega m, so there is a bit of a trade-off, there is a bit of a flexibility there. And I think depending on how we tune this and how we say, let's take a look whether the fits are actually fitting the same stuff, or whether we have to synchronize with probes at higher redshift, it is possible that maybe we can explain this away. This would be my argumentation to say, maybe this is possibly just an anomaly that may go away.
I don't know. I feel like I'm going to push back in the opposite direction now to about the large structures. I mean, they measure what they measure, right? And they are measuring something that within lambda CDM FLRW should have a particular value based on the CMB, and they're not getting that value. Outside of FLRW, maybe, yeah, they're not measuring the Hubble flow, and the Hubble flow might still have 67 kilometers per second per megaparsec, and there might be something local that is causing it to be 73. But that something local that's causing it to be 73 is not something within lambda CDM FLRW, unless it's, of course, a systematic in the measurements. But when you say maybe it'll go away, it doesn't seem possible without it being a mistake in the measurement somehow. That
I think it could be a desynchronization. I mean, if we take a look at what we are probing in the local universe, everything is calibrated on probes in the local universe. And this still has to talk to the CMB out there at high redshifts. And so my suggestion would be that we use baryon acoustic oscillations, which are on a large scale, which are large scale effect, and which can be tracked through whole cosmic history. And if we actually start to do this inverse distance ladder, starting from the CMB and then coming backwards, you actually see that probes suddenly make sense if they are synchronized with respect to each other. So my hope is that if we synchronize all the probes on baryon acoustic oscillations, we may at least understand whether it's a synchronization problem or whether it's actually something beyond Friedman, Lemaitre, Robertson, Walker cosmologies, and we have inhomogeneities to tackle. Because if we are just like missing that we have independent probes, which do not question the same part of the universe, I mean, if we are in the perturbation level, we have a lot of stuff moving around. How do you define the homogeneous background? Where is it? So you start with a local anchor, you start with local distances, and you make sense in your neighborhood. But this needn't be exactly the same homogeneous background because you are in the perturbation level. Then you start at the CMB, where you already have a very clear notion what your background is, because the fluctuations on top of it are so small. I mean, there are hints when you look at galaxy clusters and at selection effects, you find out that you are kind of like prone to over smoothing stuff. So like to kind of like if you're looking at the late universe, you have a perturbation level and you are prone to set your background lower and to see more structures, like to see more galaxy clusters there. But if you kind of like make your background a bit higher, your galaxy clusters will get less and you will have like less massive galaxy clusters, but therefore you will increase your overall background. And I think you have a little bit of a tuning choice where you set your background and how large your masses on top will be.
I guess I'm not really understanding what this synchronization problem could be within FLRW. If I say the universe is FLRW, and especially if I then say it's also lambda CDM, H0 is the same everywhere. And one might think that we were in, like a gravitational well or the opposite, a void, I guess, and that our local expansion rate would be therefore larger than the homogeneous background's expansion rate. But again, within FLRW, people have done simulations and looked at the variance. And if we were in such a deep void that we would get this level of variation, that itself would not be expected within lambda CDM. And also, we should be able to measure that we are in such a void independently. We should see a deficit of matter around us. So I totally agree there could be a kind of synchronization issue, that the local FLRW might be somehow different to the global one. But that in itself is not an FLRW. That's a patchwork of two different FLRWs. So it's still beyond FLRW.
Exactly, that's what I mean. There was this nice paper by Brent Tully for the cosmic flows, and they had this degeneracy. What do I call a peculiar flow on top of a linear expansion with h0? And then you could see how the peculiar flow velocities would change if I change my h0. And I think that's exactly the point. In the local universe, we have a problem. What is our background compared to what is our, foreground peculiar velocities? And we have a certain degree of freedom there. And the question is, how does this fit to the early universe, where we do not face this problem and we just have more or less a unique solution for that? But let me now come to the final potential nail in the coffin, as the inhomogeneous cosmologists would say. We cannot do this without talking about the Ellis-Baldwin test, for sure. This is the last test that I would like to show. I call it meta test number 2. And I think this is a pretty neat approach. And it has been put forward by Ellis-Baldwin already in 1984, when there were hardly any data. So I think this is a very good theoretical approach put forward in order to test the cosmological principle. And it's pretty simple, because in FLRW models, we expect that we have a global fundamental observer, so we have a global rest frame. And of course, we can ask, if we live in FLRW, we should find such a rest frame, and we can ask, from which redshift onwards are we converging to this rest frame? And pragmatically, I would say, whether there exists one or not, for us, may not be known, just because we do not know what the truth is as a cosmology. So let's just be pragmatic and define the CMB frame as our global fundamental rest frame. And I think we are lucky that this is possible in the first place, because when we take a look at the observations of the CMB, we of course see dipole and some slight hints at other higher orders. But this comes from our observer motions from the Sun moving around in the Milky Way moving around in the local environment. But if we apply a simple boost with a given amplitude in a given direction, then we find that we boost ourselves into a reference frame from which we see the CMB as homogeneous and isotropic to a relative precision of 10 to the minus 5. And this is amazing. And so we can say, let's assume that this is our fundamental reference frame. Then we can compare the reference frames at lower redshift, and we can ask, can we apply the same kinetic boost as we did for the CMB frame? And do we then see all of the meta distribution in this frame homogeneous and isotropic? So more or less, isotropy is here the most important point. Homogeneity is always hard to test. And so this has been one of our co-authors, Ashoka Singhal. He was the first one to do this test, and he found, no, we can't. And I think he had a hard time checking all the data again and again in order to come to the conclusion, no, there is an issue. And since then, there have been a lot of groups, and there has been a lot of havoc caused by this, no, we can't. And the most recent one, and I think the most relevant one, because they have a lot of data, is the approach by Nathan Seacrest et al. From 2022. But they also had a paper in 2021, which was like the predecessor of this one. And Nathan is really, he's an expert on data. So he takes into account all the observational biases. He knows the survey strategy, like the sampling of the telescope. And they had put together over 1 million quasars from the CatWise survey and later on from the WISE survey. And they asked, what kind of boost do I have to apply in order to bring all of these quasars to an isotropic reference frame, like the Ellis-Baldwin test wanted to have it. So they did this. And they also did simulations, very sophisticated simulations, taking into account the correlations in the data and taking into account all the systematics that may be an issue here. And they found that they are at a 4.4 sigma discrepancy for the quasars. What do we expect if we live in a lambda CDM universe? And what do we actually measure, which is out there? Then you can say, okay, this is just for the CatWise or the WISE sample. What about other wavelengths? What about other probes? And there you can take a look at radio galaxies, and there have been a lot of different surveys, but the most significant one is the NVSS survey. And here again, if we simulate what do we expect in a Friedmann universe and what do we actually measure, we are again at an excess amplitude in the boosting dipole that we need to get to an isotropic frame here, which is at a discrepancy of a bit below 3 sigma. And now Seacrest et al. Combined these two data sets, and they found now we are at a 5 sigma discrepancy that actually what we would expect as a boost in a Friedmann universe is like at 5 sigma tangent to what we actually need in the data, from the data.
Can you just maybe go into the details about exactly what they're measuring about the quasars that is anisotropic?
Yes, so it's a number count, and when you go into the reference frame, you boost yourself, and then you have like an increased number of quasars that you see due to the boost in this direction, and you have less quasars in that direction. And so you kind of like have to take into account how does the number count change and the luminosity, including the luminosities that we see or that we do not see, depending on how fast we boost, in order to get an isotropic picture of number counts of quasars.
So the idea is that if you weren't moving with respect to some hypothetical at this stage isotropic background, well, then you would see an isotropic number count. But because you're moving, you see an anisotropic number count because stuff gets redshifted, and therefore your telescope, which can only see a certain amplitude of light, sees more quasars in the direction you're moving because of the Doppler shift. So you do actually expect to see a dipole because of our motion, and they're saying that the dipole you see is not the dipole you expect. Not that there is a detection of a dipole, but it's the wrong dipole.
Exactly. So we have an excess in the amplitude so we would expect a lower amplitude in the dipole than we actually observe. So we need a larger boost in order to see a homogeneous, an isotropic distribution of quasars and of radio galaxies as well. And that's why they took this NVSS survey in order to combine the two data sets to say it's a multiple wavelength effect. It's not only for the quasars. And we can also do the same for supernovae, and we see exactly the same. So it's not just this one survey. But now you can ask, how can we attack this? So how can we make this thing go away? And the first thing, of course, is observational biases. This is what's always like an issue. But I think, talking to Nathan, he is really an expert on that, and he took into account everything, and they also simulated a lot of stuff, what the effect for the cuts on the flux, on the observed flux would be, and how far this actually changes the results for the dipole excess. Actually, this is one of the decisive quantities, but it doesn't matter too much. So you cannot make this tension go away by just like looking at the tail of the flux distribution. And if you would like to see a very systematic and simulated approach about the sampling effects and all the statistical effects that can play a role, like for instance, if we have just like due to the clustering in different superstructures, we have more quasars at certain points and we have less quasars in voids and all this stuff. This was all done by Sivat et al. And they also concluded we cannot make this effect go away by just observational biases. Then of course you can attack theory. Theory is always good. You can say, but this dipole is more or less a kinematic effect in special relativity. But the universe is full GR. So is this exactly the same equation? Can we still apply this in full GR? And here we have another paper by Nadolny et al. And they say, yes, we can. So this is also not an issue. And the last issue that, of course, is always there is a redshift evolution, because the Ellis-Baldwin test does not want to make any assumption about volume and about distances. So they just say, let's go at high enough redshifts that we do not have to take into account all these bulk flows, which are usually tackled in like Cosmic Flows project and in like our local neighborhood. So let's go to something where we think we should have converged to the global reference frame, like redshift 1 or above. And then we project all the stuff that we find, all the quasars on the sky, no matter at which redshift we are. So this projection can, of course, make a difference if we instead use redshift bins, and then we slice up all the galaxies or the quasars into these redshift bins, and we want to see, is there any evolution, for instance, in the quasars or in the radio galaxies, or in how far is the effect of the luminosity that we observe, is there any dust in this, in how far is this projection effect that we do biased? If we just do a redshift analysis, would we see something else? This has been done partly by Dalang and Bonville, so they derived all the formula. It has also been done by Roy Martins before. And this is the direction that they go, and they think we should understand the effect by taking these redshift slices, which is very important. But they do this, and they still find a discrepancy of about like 3 sigma. So they say, based on what we know now, we still have a problem with bringing this into accordance with lambda CDM.
Charles gave a cosmology talk on that paper as well.
Yes, I think I saw that. And yeah, so I think we all have a hard time to understand this. And so we can say, on the one hand, we think that the deviations come from incomplete modeling and incomplete observations. This is still possible, that we are missing some galaxies, or that we kind of like do not understand the full physics which is going on there. But this we can understand if we take a look at the redshift distribution, and then we slice this up, and then we see what happens over redshift with the dipole. And if we are looking for inhomogeneous cosmologies, I mean, this is the nail in the coffin of FLRW. Because here you can say, look, we have multiple wavelengths, we have an excess amplitude. No matter how we analyze this problem, we always see an excess in many surveys, different probes, different techniques. I mean, we have this redshift evolution, but still we see an excess, which is a totally different methodological approach, but still it's there. And so I think this is one of the points that the community should discuss. And this is, again, one of the points where we would say, if we cannot bring this into agreement, does this mean we have to abandon FLRW, or will we go on searching for systematics? And how likely is it that these galaxies change? And for me personally, I would say it doesn't matter what comes out here. The most interesting point for me is we have two different camps. One says we would like to make projection, and we kind of like have a pre-processing on the data that we kind of subtract all these biasing effects, and then we apply the Ellis-Baldwin test. And the other camp says, let's take into account all the evolution and all the stuff, not in a pre-processing step, but in the full methodology. They take this evolution in account over redshift. And I think no matter which way we go, in the end, we should agree on the interpretation and on the results, but we don't. And this is the physics that I think we still should understand and explore by talking to each other in the different camps and say, in how far can we combine what we learn from the redshift analysis and what we learn from the projected analysis?
Yeah, where to next? We've measured these dipoles, and they're somehow not where the CMB says they should be, or they're bigger than what the CMB says it should be. And there are these other things you talked about. What should we be doing? What comes next?
Well, so first of all, we have assembled a collection of hints that could turn out to be signals for cosmic inhomogeneity and anisotropy. And for us, if you take a look at the figure here, the fact that the different probes do not seem to agree on a common amplitude or a common direction beyond the expected signal, this shows that there is no obvious common bias and no systematic that we forgot in all of these data. I mean, it could have been possible that joining all the probes, we found out, everything seems to be aligned in the same direction, and then we found some physical evidence which could explain this overall systematic effect. But there is no such thing. And so, of course, the end of paper 1 here is we understood that we think there is nothing obvious that we have forgotten. So where to next is we have to find alternatives. We have to be creative and say which alternative cosmologies could now be fitted to the data in order to see whether we actually see something beyond Friedman, Lemaitre, Robertson, Walker cosmologies, or whether there still is some issue in our systematics and in our theoretical understanding of Friedman models. And the hope would be that we use models which have a smaller amount of necessary assumptions, that we actually know what exactly goes in there, or be as data-driven as possible, for instance, to have this flexible basis function approach like Asta Heinesen does, in order to probe the actual constraining power of the data and the future data that we will get. As Jim Peebles wrote in his review paper, we have empirical evidence that there is still a better theory to be found. And so I think where to next for us is, let's look for that model and let's look what we can come up with.
So maybe Asta's currently somewhere in the world doing this research, or someone else is doing it with her work. But if one takes Asta's model and does try to fit all of these, because I guess all of these are at sort of different average redshifts and things, can one fit all of these with her freedom?
I think this should be possible, but I'm not too deep into that. But I think this is still in the infancy in order to get the data so that it actually can be inserted into that framework. Because this is another issue that we think, we just realized that everything is calibrated on some simulation of lambda CDM or some FLRW model. And so if we calibrate all our data and we do not get the raw data, we will have a hard time to fit any other cosmology, because if we're getting in FLRW through the back door, we are inconsistent in that sense.
There are baby steps one can take, right, though? There's the first step, which is, I guess, the step that you're showing on the slide here, which is saying, okay, within lambda CDM, is everything consistent? The answer is no. Either there's sort of different areas going on in each of these measurements, or there's something beyond lambda CDM. And then there's the final step one can take, which is, okay, I've got this new model. Astor's model, perhaps. Let's reanalyze from the ground up the whole data now. Is everything consistent in this model? But then there's also, I guess, an intermediate kind of, it's not 100% rigorous, but so long as the other model is sufficiently close to lambda-CDM, which it kind of has to be because lambda-CDM is sufficiently close to correct, you can do a beyond lambda-CDM parameterization of the pre-analyzed data a lot of the time.
It's a kind of like effective probing, you mean? Like you take a parameter which is a little bit perturbing beyond lambda-CDM, then you look whether this goes in the right direction, whether like this can explain the right effect. And then you can still say, okay, now I'm modeling this effective parameter that I had in a more rigorous way, which is based on more physical principles. But I know that I expect the same effect as actually is in the data.
Yeah, and you parameterize the way in which things would change if you did the ground up new analysis in this new model. So long as they're sufficiently close, you can sometimes come up with a way of just parameterizing how it would be different.
And the other thing that you're kind of like inspiring me now is the people in the surveys should also have a look in how far they constrain cosmology and in how far they jointly constrain any astrophysics. Because if you take a look at a nonlinear optimization problem, it does a difference whether you first fix your astrophysics and then fit for the cosmology and keep the astrophysics fixed, or whether you say the whole bunch is a joint parameter set and now I would like to find an optimum which finds a compromise between a certain parameter set in astrophysics and a certain cosmology, because then you're using the full underdetermination problem where you can actually shift between perturbation level and cosmological background. And this is different as if you fix the astrophysics and then fit for the cosmological background.
Can I ask one more thing about this? If I remember correctly, when Nathan Sechrist and his collaborators were doing this stuff with the quasars and finding this dipole, there was a paper that came out also doing it with supernovae, and they also found an anomalous dipole, but was it not in like the other direction or something? It was anomalous in the exact wrong way or something.
Horstmann-Schwarz, and yes. This was pretty surprising because I think it even had a value which you totally wouldn't expect. I mean, this was even much less than the CMB value. And I'm not sure whether this might have been a problem. I think they used a Pantheon sample. And so you can ask in how far you actually kind of like had different effects that you accounted for twice. I do not remember which effect it was, but I think for the local bulk flows, they did not reverse what the Pantheon had done, and they still took into account that we had bulk flows, and I think it is possible that they actually accounted twice for, like 2 times the biases for the bulk flows in the late universe. And so it's possible that this is actually systematics which might go away if you reanalyze the data.
I see, because when that paper came out, in some ways it was like saying, okay, the Sechrist group might be onto something because there seems to also be some anomaly in the supernova. But in other ways, it was kind of evidence against. It was sort of like, okay, there must be unknown unknowns because these results are just all over the place in a way that doesn't seem explainable with new physics.
I think the problem with the Pantheon was that at first it was like not clear how you could reverse all the biasing pre-processing steps that the Pantheon people had done. And this is why Ashok Singhal, he did not use the Pantheon, but he used the predecessor survey where every step was clearly written out and he could reverse all the steps so that he got to the raw data in the heliocentric frame. And then he started from scratch and said, okay, now I would like to analyze this again. And he also got an excess dipole amplitude. So it's possible that if you actually go to the raw data of the Pantheon and you start again analyzing all the steps from scratch, that you again find an excess dipole amplitude. And this was just like because you didn't correctly reverse the stuff that they had done. So what should change? I think we should definitely have the conversation and the discussion which biases and new physical effects and variations of lambda-CDM we are willing to add to resolve the tensions, and which observational evidence will convince us to abandon lambda-CDM in favor of an alternative. And I think in order to achieve the best outcome, both camps, the ones in favor and the ones against keeping lambda-CDM, they should jointly investigate the degeneracies that we have in the interpretations and exploring these remaining degrees of freedom in this underdetermination problem with an open mind and for all possible ways how to fill in the gaps. I think this will give us an understanding which will actually resolve the tensions in the end, so that we kind of like find an overall agreement on the interpretation.
You asked the question, what evidence will convince us that lambda-CDM is wrong? It has to go both ways, right? There has to be this what evidence, but also what alternative model. Because, as you said yourself, H0 tension is now 5 sigma, right? Like, that's supposed to be the threshold. And so if you'd asked everyone in advance, what's the threshold? Oh, it's 5 sigma. Okay, well then it's done. We're done. We throw away lambda CDM. The problem is no one's come up with an alternative model that works to explain the H0 tension, in which case we're still stuck with lambda CDM. And for me, the answer to your question is when there is an alternative model that in some wishy-washy combined way fits the data better, but is also quite well motivated, that's where we do it. And everyone will side with that, I guess. And lambda CDM had its own moment with that in like the very early 2000s when the first supernovae distance ladder measurements came in, and it was like, okay, there is this vacuum energy problem of we don't know why it's this value, but it is just one parameter, and it can sit there within the mathematics. It's fine. And wow, okay, all of a sudden all of the data at the time fits so much better than a kind of open universe model or things like that. And at the moment, we're waiting for that same simple parameterization model that actually pulls all the pieces together and works. I think if someone was to write down a model that actually solved the H0 tension, that revolution would happen overnight almost, because everyone's aware of it. But there is no solution that is a well-motivated model that kind of works.
Personally, I would hope for people to doubt our knowledge based on the models a bit more. And if we try to set up a more data-based approach whenever this is possible, we pay the price that we will increase our confidence bounds. But these confidence bounds will actually resemble our true knowledge based on the data. Because my big worry is, what's it worth if we attain a percent precision cosmology, but this percent precision mainly rests on potentially incomplete and even incorrect models? What have we won then? And so I'm fine with less percent precision cosmology, but it's purely data-based, and we do not have to kind of like rewind all the time when we think our model is incomplete.
Last question, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
Theory, of course. I mean, it's theory, because I think that currently there is a certain hype for methods based on artificial intelligence. And I think if we're pursuing only that, we will be giving up a highly important aspect of our own understanding. Artificial intelligence and artificial neural networks, for me, are mere tools like basis function approach, basis function expansions. And they're very good at doing comparative searches for new objects or to enhance the data set for a quick data mining and set up similarities. I mean, I've done my PhD in image processing. I can stick my neck out here. So I think they're really good as tools. But they lack explanatory power in terms of fundamental physics. I would like to know from fundamental physics, how can I resolve the tensions? How does a basis function expansion tell me this? I mean, this is exactly the same for neural networks. If I want to answer the question, why? Neural networks will not give it to me. And that's why I think we should still focus on our human understanding in order to see how can we explain these tensions. And it's still valuable to go back to all the previous approaches that we had to the literature and to fundamental principles, because my colleagues and I from strong gravitational lensing, we went back to the fundamental formalism, and I succeeded in deriving the most general class of degeneracies in this formalism, understand it as an effective theory, and then we were able to set up an approach which immediately tells us which lens and source properties we can derive directly from the data, and where we have lens models or in general model assumptions to extrapolate into regions where we do not have any data. So we separate the database knowledge from the additional model assumptions, and we know which role all of this plays. And this was possible by just going back to fundamental principles and to understand the formalism again. So I think a fresh look at the theoretical foundations and the vast literature can have an impact and gives us new insight so that we can more efficiently, and I mean sustainability is definitely an issue, that we can more efficiently analyze the data, and we know where model assumptions play a role and where the data actually drive our inference processes.
Okay, thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for this channel and for yourself, because YouTube will know to recommend more stuff like this. And share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, we talked about Asta Heinessen and Haley McPherson's talk quite a lot, at least the work based on the talk quite a lot in this talk. Maybe you want to go and check that one out now. And thanks, Jenny, for the great talk.
Thanks for the invitation, Sean. It was a pleasure.